Thank you for joining me on this unit circle video where I'll be missing from the lesson, so I'm hoping this will help you out. First, I just want to remind you of a few important things. So here's a unit circle, and that means that each of these points is 1 away from the center. 1, 1, 1, and 1. Not that that matters too much. And then, on this unit circle, we might have a particular point, which we call P, X, Y. So you remember I was going through this recently. So if I draw a line from the center to Px, y, you can see I can create this right angle triangle here. And this angle we denoted as theta because we started our measurement of 0 degrees from the positive x-axis. And we went in an anti-clockwise direction. So this was 90 degrees, 180 degrees, 270 degrees, and then 360. Now it doesn't just stop there. We can represent angles that are greater than 360, or if we go in a clockwise direction, we can represent negative angles from 0 as well. Now you'll also remember, just very quickly, that you can denote these angles in radians as well. So here we have 0 radians, pi on 2, pi, because pi radians is 180, 3 pi on 2, and then we're back to 2 pi, and so on and so forth. So we're saying that Pxy is a point on the unit circle such that theta is the angle between 0 and as far around in the anti-clockwise direction that we've gone. Now, theta is important here because it's the one that represents how far around we've gone. So everything is going to be based on our distance theta, and we'll be using it quite extensively. Let's build some facts within this triangle though. So first of all, obviously the hypotenuse length is 1 because it's on a unit circle. Secondly, we have this height here, which we can write as y, and this length, which we can write as x, because as you see, we've denoted p as x, y. And if we use a bit of trigonometry within this right angle triangle, you'll see that sine of theta is equal to opposite over hypotenuse, which is y over 1, which just equals y. And cos of theta is equal to adjacent over hypotenuse, which is x over 1, which just equals x, not y, x. And then tan of theta is equal to opposite over adjacent, which is y over x. And you'll notice here, not that this is that important for this lesson, but if I take that fact, tan of theta is equal to y over x, well that means that tan of theta is equal to sine theta over cos theta, using our two facts here and here. So keep that in mind. That is a trig identity that we'll come back to in a few weeks or a month or so. So we have our important information here. Y is equal to sine theta and x is equal to cos theta. And so we can write down Pxy as the point P cos theta, comma sine theta. And that will come in handy later as well. Most importantly though, notice that sine theta here is the height that that point is above the x-axis. And cos theta here is the length away from the y-axis that point P is. And that will also be important. So cos theta represents a displacement on the horizontal axis, and sine theta represents a displacement on the vertical axis. And so that will come in handy for us later on. And it will also help you to bring these ideas across to our trig graphs that we'll get to. So what we have is some angles that are all equivalent. So I'm just going to draw another point here, another point down here, another point about here, and just draw a little cross that goes to the center, there and there. And I can make a little rectangle out of this. Again, what happens is it does start to get a bit confusing the more I add to the diagram. So I'll have a summary diagram in a minute as well, but you can also pause just to help you. So we have these points, and within this, you'll notice that because of a whole bunch of our geometry from year 8 and year 9, theta holds here in 4 different locations. So we have some vertically opposite stuff, we have some angles within parallel lines where these are parallel and these are parallel. So maybe take a minute just to convince yourself that those thetas are all true. And because of that, we have some equivalencies. We know that this height is the same as this height. We also know that this length is the same as this length. And we have the same thing with this height, except it's negative, and this height, except that's negative. So we have these points here, which I'll call P1, P2, and P3, where we have some nice angular equivalencies. And that will become important as well. We've talked about this a bit in class also. So our height here is equivalent. So this is also sine theta. But you'll notice here that this is negative sine theta because that goes below the x-axis. And this is also negative sine theta. And equally, if we go as our width, we have cos theta there, so that's positive. But we have negative cos theta because it's below the y-axis. Negative cos theta here, below the y-axis, and cos theta. And so now we have this nice rectangle where you can clearly see that cosine is positive in this quadrant, and sine is positive in this quadrant, and this quadrant. And equally, if you go around and do the testing, you'll notice that tan is positive in this quadrant and this quadrant. So it's probably about time that I gave the quadrants some names, just remind you of those names, and then bring you forward with this rule. So first of all, this is quadrant number 1, quadrant number 2, quadrant number 3, and quadrant number 4. And it might seem a little bit like we've pulled those numbers out, they don't follow any particular order, but you'll notice here that this follows out starting from 0 here on the positive x-axis and moving in an anti-clockwise direction. Now in quadrant 1, all of the ratios are positive. In quadrant 2, sine is the only one that's positive. In quadrant 3, tan is the only one that's positive. And in quadrant 4, cosine is the only one that's positive. So now we call this, I learned it as all stations to central, starting from quadrant 1, but also, and the textbook uses it quite frequently as the cast diagram. So we get this idea. A cast diagram, where you just draw your little shape like that, starting down there in quadrant 4, CAST, and it tells you who is positive where, and that will help in the long run as well. So we have our cast diagram development. Now you see our diagram's got a little bit of a hand. Let's have a look at the one that you have access to in your textbook as well. So this is the textbook diagram, and you notice here that they've done a few things. First of all, they are only using radians, so you have to keep that in mind, and we're going to head more and more towards only using radians. Then they've also got this idea of negative y, negative x, y, and x to help you understand as well. So you can see where that sine, because sine is y, and we have that link here, is positive, and you can see down in the bottom where it's negative, and the same with x and cosine. The other important thing they have that I didn't have was this idea. So we've got p of theta, so a point represented by this angle theta, and then we have this p of pi minus theta. So that is related to the fact that this is pi and this is theta. So if we move backwards from pi by theta degrees or theta radians, we get to a point that is p of pi minus theta. And equally, if you start at pi and move down, you get to a point of p pi plus theta. And over here, you start from 0 and move down, you get to a point of negative theta, or if you start from 2 pi and move backwards, you get to a point p of 2 pi minus theta. So it creates these really nice rules for us. First of all, well actually, I'll do it on here. Let's just add our cast diagram, C-A-S-T. Now, there are rules associated with each of the quadrants that we can use, and in the textbook it's written down as a list of 12 rules, but realistically, if you understand the unit circle, you don't have to know any of these rules, because the unit circle will guide you in that. So let's write down these rules. First of all, they are all equivalent in the first quadrant, so I can just write down here sine theta, cos theta, and tan theta. They all start as those values in the first quadrant, so that's not overly interesting. But it's when we get into the second, third, and fourth quadrant it starts to get interesting. So in the second quadrant, our point P is not P of theta anymore, it's P of theta minus, pi minus theta. So we have this rule. I'm going to rub out that S and perhaps put it somewhere else. The first rule is that sine of pi minus theta, or 180 minus theta, is equal to sine of theta. So the angle, the equivalent angle in the second quadrant, is equal to that angle in the first quadrant, and it's still positive because sine is positive in that second quadrant. So I'll just throw my little S here. But cosine and tan are negative. So cos of pi minus theta is equal to negative cos theta. And tan of pi minus theta is equal to negative tan theta. And so we have the same thing in the third and the fourth quadrant. And again, I'll rub out these cast diagram symbols and replace them. We have sine of pi plus theta. Now keep in mind tan is the only one that's positive, so it's equal to negative sine theta. Cos of pi plus theta is equal to negative cos theta. And tan of pi plus theta is equal to tan theta, because that's positive in the third quadrant. And the same over here, sine 2 pi minus theta is equal to negative sine of theta. Cos 2 pi minus theta is equal to negative cos theta. And tan of 2 pi minus theta is equal to negative tan of theta. And you'll notice here I've actually made a little bit of a mistake. It's not negative cos of theta, it's positive cos of theta, because cos is positive in the fourth quadrant. So I'll just put my T back here and my C. So we've got our cast diagram back. And they are the 9 rules that you'll see in your textbook. You'll see referenced in different examples. You don't really need to know these rules though, because you can just use a unit circle to generate them, which you have been doing in exercise 5C already. But we have those 9 rules in case they're needed. So that's really the extent of it. We can relate any angle now. For example, if we take the angle sine of 139. Now it's not one of our exact angles, but we know that sine of 139 is equal to, so it's in this fourth quadrant, so I'll just draw a quick unit circle, and you should be doing this every time. And there's my circle. Sine of 139 is here. And from that, to get to 180, I have an angle of 41. So we know that sine of 139 is equivalent to that 41 there. So it's equal to sine of 41. And sine, of course, is positive. So it stays as positive 41. We can relate any angle, or you can use this idea here, as long as you identify the quadrant it's in first and then use the appropriate setup. So there we have it, cast diagram and all our relationships. I'm going to do one quick example. I've got a unit circle here and show you how this could work in this case. But just remember that it really doesn't become an overly helpful tool until we get to the point where we're solving equations in about a week's time. Once we're doing that, it's really super important that we can do these skills. We'll backwards design this skill. So let's imagine that I tell you that cos of theta is equal to 0.69. Now you could obviously use a calculator and backwards design that answer just by doing cos inverse. But we don't need to do that to find different positions within our unit circle. So I'm going to just draw an imaginary point here, and I'm going to say that this is theta. And so cos of theta equals 0.69. And remember, with cos, that means that this length here is 0.69. And that's a representation. It's not overly important for us solving these questions coming up. So question A. If cos of theta equals 0.69, what is the value of sine of pi minus theta? So here's a nice question. Now, it actually turns out that 0.69 is important, which I neglected to keep in mind here. So sine of pi minus theta is over the back here. and this is our angle pi minus theta, and this value here is theta, of course. Now, sine of pi minus theta is equal to sine of theta. Because of our cast diagram, sine is positive in that second quadrant. And so sine of pi minus theta equals sine of theta. That means we need to calculate the value of sine of theta. And this is where a little bit of Pythagoras Theorem will help us. Let's call this value y. Now we know that y, which is equal to sine theta, that height from our work earlier, y squared plus 0.69 squared will equal 1 squared. And so we can calculate this. Y squared will equal 1 minus 0.69 squared. And if you quickly want to grab a calculator and check that you get a similar answer to me, and I get y is equal to 0.724. And so sine of pi minus theta is equal to 0.724. Now let's have a look at question B, which is actually a little bit simpler. Cos of 2 pi minus theta, simply because we're working with that cos. So if I just drop my line down to here, that's my 2 pi minus theta. It's in the fourth quadrant, and drop a little dotted line there. You'll notice that cos of 2 pi minus theta is equal to cos of theta. That's the relationship there. But we have to check whether it's negative or positive. Cos is positive in the fourth quadrant, so it's just straight up equal to cos of theta, which is 0.69. And then question C is, what if we're dealing with a tan of theta? So tan of pi minus theta in this case. Well, tan of pi minus theta will be equal to tan of theta. So again, we're over in the second quadrant here, but in the second quadrant tan is negative, so it's negative tan of theta. We just need to calculate tan of theta. Now, tan of theta in this case will be opposite over adjacent, so it's negative sine theta over cos theta, because that's our opposite over adjacent, where this is cos theta. And we know the values for those, so it's negative of 0.724 over 0.69. And so we just calculate that, and we get it's equal to negative 1.049. And so you can calculate all values, sine, cos, and tan, if they're the equivalent, one of the equivalent 3 values to an initial value in the unit in the first quadrant, then you can calculate those. Keep in mind, of course, a couple of things. Sine of any angle and additionally cos of any angle should be between negative 1 and 1, so they don't get greater than 1 or less than negative 1. But tan, of course, can be any value. And that relationship you get from the initial unit circle. So keep that in mind as well, that sine theta is the height, cos theta is the width, and tan theta is opposite over adjacent, so it's sine theta over cos theta, and that will always help you to link those. Later this week, we're going to talk about reading off the vertical axes, and so I'll teach you how to another way to relate cosine and sine together by reading off the vertical axes to get that link. Well, thank you for listening, and all the best.